In this session, we are going to find the energy in rotation motions. So kinetic energy of a rigid body object we are going to discover. We consider this blue shape of the rigid body object we are going to consider. This object is making circular motions around the axis of the rotation. Rigid body object is divided into the number of pieces, like this. Then we only consider this blue part. So making a circular motions around the axis of the rotation. Kinetic energies of the circular motion of the single piece of the rigid body object can be expressed 1 over 2 m sub I is the mass of this single piece times the velocity squares. And if you sum up all the kinetic energy in all the regions, then you can find the kinetic energies of the rigid bodies. Then each point, the angular velocity is the same, omega. As I explained, angular velocity of every point inside of the rigid body is exactly same. So we can use the same omegas. Distance from the axis of the rotation, we choose r sub I. Then velocities. Linear velocity is expressed v sub I equal r sub I times omega. Then you can substitute here. Then rotational energy is expressed k equal 1 over 2 I omega squares, because omega is a constant. K sigma 1 over 2 m sub I b sub I squares. So you can substitute b sub I equal r sub I omega. Then 1 over 2 m sub I r sub I square omega squares. And then 1 over 2 and omega square is a constant. So you can move the outside of the sigmas. M sub I r sub I squares. And if you name that this is I, moment of inertia, this energy, kinetic energy of a rigid body is expressed 1 over 2 I omega squares. So we name it I, the moment of inertia. The moment of inertia has the same role as a mass. When we consider the rotational motion of an object, instead of mass, we use the moment of inertia. The moment of inertia is expressed using this expression. If you consider two objects, the moment of inertia of this system of the object, moment of inertia is expressed m sub 1 r sub 1 square plus m sub 2 r sub 2 squares. So you can sum up all the mass times the square of the distance to the axis of rotation. So this is the definition of the moment of inertia. We could consider slender rod. Density of this slender rod is exactly the same of the rho. Then total mass of this slender rod can be calculated. Total mass is the density times the length. Length is L. This is L. Then center of mass is located at the middle point of the slender rod. So we choose x equals 0, corresponds to the center of mass. Right end of the slender rod is located L over 2, and the left end of the slender rod is located minus L over 2. Then we'd like to calculate the moment of inertia. As we showed, we divided into the number of the pieces of the slender rod. This is we have to do the first thing to do. Then we consider the single segment of the slender rod, dr, distance. Then the mass of this single piece is expressed the density times the distance. So density times the distance is a dr. So this is the mass. And the distance, center of mass, is expressed x. So moment of inertia can be calculated. X square times the mass. Mass is a rho dx as I explained. Then you can substitute. Then perform the integral. X square rho dx. So it becomes 1 over 3 rho x cubed L over 2 minus L over 2. And then you can calculate. It's becoming 1 over 12 rho L cubed. Then you can substitute. Total mass is expressed as rho L. So moment of inertia of a slender rod expressed 1 over 12 times mass times the length square. Then finally, I'd like to explain parallel axis theorems. So in the last case, we obtained the moment of inertia when the axis of rotation passes through the center of mass. But sometimes the axis of rotation does not pass through the center of mass. Then we'd like to find out the relation between the moment of inertia when the axis of rotation passes through the center of mass. Axis of rotation is located in very different places. Then we'd like to find out the moment of inertia with respect to the new axis of rotation. In this case, the center of mass is located at the origin. So distance from the axis of the rotation. This distance is expressed square root x sub I square plus y sub I squares. Right? Then we'd like to calculate new axis of the moment of inertia. Then this distance we need to calculate. X doesn't change. So x sub I doesn't change. But for the y component is changing. So y sub I minus d squared. So if we expand, it produces 3 terms. Center of mass of the y component is defined m sub I, y sub I divided by the total mass. In this case, we choose the center of mass is located at the origin. So this is going to be equal to the 0. So from this equation, you can find if you multiply the m sub I and the y sub I and sum up, it becomes 0. So we can return to this equation. So last terms it becomes 0 because of the I explained. And the first 2 terms, this corresponds to the actually I sub cm's. But we still have a d squares. So d squares is expressed md squares. To find out the moment of inertia around the new axis of the rotation, we have to find out the distance between the 2 axes of the d. Then by adding the md squares, m is the mass of the rigid body object, times the d squares, you can find the moment of inertia around the new axis of rotation. md squares is always a positive quantity. So from this actually rigid body has a lowest moment of inertia about the axis through its center of mass. Okay, moment of inertia I sub cm is the lowest values because the second term is always positive quantities. Okay, this is the end of this session.